Thank you, Peter. Okay, I'll move on to the first slide. Okay, my first slide, most of you are probably familiar with, but shows the full extent of the Mount Isa province on a combined gravity and magnetic 1VD image. It illustrates that only about a third of the province is exposed. The rest is hidden by cover, the outcrop extent being shown by the yellow line. GSQ has subdivided the province into a number of structural domains that are generally bounded by major structures and have responded in different ways to the main tectonic events in terms of their depositional history and their response to the later deformations. Using the geophysics, it's possible to make an attempt anyway at extending the structural domains under cover. This is a bit more simplified map of the province. The extent of outcrop, again shown in this case by red. As the title of my talk indicates, I'm going to be talking about the eastern half of the inlier, or the province, the area to the east of the blue area, which is known as the Western Fold Belt. The Eastern Fold Belt consists of the Mary-Kathleen province, domain, which is shown in pink, and the other domains, which are lumped together in the more flesh-coloured tones. I'm also going to talk about the central basement belt, which is the Chalcodon-Leichhardt domain, shown in orange. Those of you who worked in the Mount Isa area prior to 2005 will probably be familiar with the breakdown of the succession into what were called cover sequences, cover sequence 1, 2, and 3, which overlay a basement that was deformed during the Barramundi orogeny around 1900 million years. I'm not going to talk about this in detail because it's largely superseded by what I'm going to tell you, but it's just a bit of the background. This framework was put together by David Blake in 1987, and it was based on the work that was done by joint BMR-GSQ parties between 1968 and 1978, which followed on from the work of BMR and GSQ in the 1950s. Although the mapping was first rate, considering the time that was done, there were some deficiencies in that detailed structural studies weren't really attempted, and also the dating, isotopic dating in those days was more in its infancy. It was mainly rubidium strontium, and there was some uranium lead, but it was the old-fashioned bucket type uranium lead dating. Shrimp dating was only just becoming available at the time this was put together. Subsequently, BMR and university groups undertook some detailed structural studies in a transect from Mount Isa to Cloncurry between 1988 and 1992, and this resulted in a bulletin which was published in 1992 edited by David Blake and Alastair Stewart. Following on from that, there were numerous PhDs, honours theses, and staff research, mainly from JCU through the 1990s and 2000s. And in addition, there were structural studies by Monash and Melbourne University as part of the Australian Geodynamics CRC in the 1990s. That particular study included a deep crustal seismic survey that was done by AIG-GSAQ, which is BMR's successor, shot in 1994. Shrimp dating was becoming much more available, and a lot of it was done through the 1990s, particularly by Rod Page at GA, or AIG-GSAQ as it was, and others such as Giles and Betts. Following on from those studies, there was the Predictive Mineral Discovery CRC, or the PMD CRC, from 2001 to 2005, and that incorporated work by a variety of university, government, and industry researchers. In the Eastern Succession, this included detailed structural studies, particularly by George Gibson, and shrimp geochronology by Narelle Newman. particularly using detrital zircons, which started to help unravel the of the stratigraphy. There was still JCU was still involved, and particularly Mike Rubenak and Tom Blenkinsop, who was there at the time. Revised mapping by GSQ started in 2005, and that's when I became involved more deeply with Mount Isa as part of that project. It utilised a lot of the geophysics that was available, and we did further shrimp studies through GA, particularly by Chris Carson and Chuck McGee, and that helped refine the work that Narelle had done. Since then, there's been more detailed studies by JCU, partly funded by GSQ, and GSQ itself has also done some detailed structural studies, particularly in the Mary Kathleen Belt, but also in the down in the Selwyn Belt, which I was involved with since I retired. And of course, over the decades since the 1950s, there have been literally thousands of exploration projects ongoing, still ongoing, and that's greatly increased our knowledge of the province. An indirect contribution to our understanding of the Eastern Succession was the work done in the West by sequence stratigraphic analysis and shrimp dating as part of various projects. One called Neighbour, there was a Myra P552, and the PMD CRC. All this was done up to 2005. Now, that's a pretty detailed image, and given the fuzziness of this projector, it's pretty hard to read. So this is probably shows you the main take-home elements. The succession through the province has been divided into three super basins: the Leichhardt, Calvert, and Isa super basins, separated by inversion events. And within these super basins, super sequences have been recognised. These are the units there shown in red, and they're separated by hiatuses, which are the areas of vertical stripes. Although this was derived in the Western Succession, it's provided a framework to try and understand what's going on in the Eastern Succession. So now, working our way through the Eastern Succession, starting with the basement, which is exposed in the Kalkadoon, Leichhardt, and Mary Kathleen domains. It includes poorly understood migmatite complexes deformed during the Barramundi orogeny around 1900 million years, and they're overlain by the Leichhardt volcanics and intruded by coeval Kalkadoon and Ewan batholiths. These are all dated around 1865 million years. The Leichhardt volcanics are felsic. They're commonly strained, as in the photograph there. And as well as volcanics, they probably do include high-level intrusive rocks. The strain and high metamorphic grade is most developed in the south and drops off in the north. And I've spent quite a bit of time working in that area where the strain's weaker and where you can actually see the original character of the rocks a lot better. For example, textures like Fiam and ignibrites are quite well developed. These photos are all from the Kajabi-Dobbin area. The photomicrographs of the samples from the outcrop shown in the photograph, and one of the features is the fact that the feldspar and quartz are all broken fragments. They're not neat phenocrysts, and that points to the rocks being volcanoclastic. You see stretched Fiam and even eutaxitic textures in some of the rocks. And in the bottom case is what I interpreted as an accretionary lapilli tuff. In addition to the more clearly volcanic rocks, there are intervals of conglomerate and graded sandstone beds. So all of these lead me to think that it's just simply a volcanic sequence with some interbedded sediments. The conventional interpretation is that the Leichhardt volcanics are overlain by the Magdalene metabasalt, which has been equated with the Eastern Creek volcanics, which are shown in the olive green colour in the western part of the map on the slide. These are in the Leichhardt River fault trough, or the Leichhardt River domain in the GSQ nomenclature, and are a significant unit in the western succession in the Leichhardt superbasin. If this correlation is valid, then the Magdalene metabasalt would be about 1780 to 1790 million years, and represents the rifting event at the start of the deposition in the Leichhardt superbasin. However, it's not been dated, and could still be part of the magmatic event that's related to the Leichhardt volcanics, the earlier event. Conflicting with my evidence of the rocks being a volcanic sequence that I've based on the north, my colleague Bill Perkins has proposed that the Leichhardt volcanics are primarily intrusive and actually intrude the Magdalene metabasalt. This is based on his interpretation of complex outcrop patterns evident on satellite images and on some of the older mapping in the southern part of the area down to the south of Lake Mary Kathleen. The strain there is a lot greater, and the relationships, I think, are probably harder to determine. I acknowledge that the Leichhardt volcanics probably include high-level intrusive rocks, and in fact, with my experience in working in Phanerozoic volcanic successions in eastern Queensland, I'd be surprised if there aren't intrusive rocks in there. But I'm still skeptical of Bill's interpretation, but we agree to disagree on this. Some of the complex outcrop patterns were interpreted by Dave Blake as thrust duplexes, and Blake also pointed out that it's often difficult to tell the difference between the volcanic rocks and intrusive rocks, mafic rocks in that area. I think some of the outcrop patterns are probably equivocal, and it's not clear what's intruding what on satellite images. And some of these mafic areas might, rather than being volcanics, may be feeders or subvolcanic intrusives to the Magdalene metabasalt, and in fact they're intruding the Leichhardt volcanics rather than the other way around. Anyway, this needs more, I think it probably needs more work to confirm this one way or the other. And the other thing is that it'd be good to actually date the Magdalene metabasalt. It's very difficult because it's basalt, and basalts don't really have a lot of zircon usually. But there are sediments interbedded with them, and maybe some detrital ages on those might help. Anyway, overlying the Magdalene metabasalt, whatever its age, is the Argilla Formation. It again is a largely felsic unit, and it's been dated at 1780 million years, about 80 million years younger than the Leichhardt volcanics. In most places, they're separated from the Leichhardt volcanics by an interval of Magdalene metabasalt. So they're probably roughly time equivalents of the Eastern Creek volcanics. However, it can be noted that in the western succession in the Eastern Creek volcanics, there are no felsic volcanics whatsoever at this time, but nevertheless, the Argilla Formation must be in some way tied in with the rifting event that's associated with the initiation of the Leichhardt superbasin. Again, in the less strained rocks in the Kajabi-Dobbin area, you've got preserved igneous textures, volcanic textures such as stretched out fiam, broken crystal fragments, and in addition there are well-bedded volcanoclastic sediments such as in the bottom. In places, as well as what I interpret as ignimbrites and volcanoclastic rocks, there are flow-banded rhyolites, such as here they've got flow-banded rhyolite and serolitic rhyolite. overall, it's just a fairly typical volcanic felsic volcanic sequence. In contrast, as you go further south, the strain increases, and you have biotite schists and gneisses, and these are illustrated in this figure here. The felsic biotite schist is just to the north of Mary Kathleen. The Argilla Formation is overlain by the Ballara quartzite, which is shown as a very thin yellow unit on the map, and in turn that's overlain by the much more extensive Corella Formation, which is a sky blue unit. The Ballara quartzite is commonly only 100 to 200 meters thick, and in places it lenses out entirely, reflecting relief, I think, on an unconformity surface. The unconformity, or the contact anyway, is quite well exposed in places, and often there's a basal conglomerate, and in places that basal conglomerate consists of or contains clasts of the underlying Argilla Formation. Otherwise, the Ballara quartzite is dominantly a quartzose sandstone, often with quite well-developed crossbeds. Detrital zircon ages from the Ballara quartzite largely reflect the ages of the underlying Argilla Formation. So you get a lot of 1770, 1780 million year zircons, and of course components from even older, from the Leichhardt volcanics and Chalcodone batholith. However, there's a tuff was dated supposedly from the Ballara quartzite near on the highway near the East Leichhardt Bridge, gave an age of 1755 million years, although the rocks there aren't typical of the Ballara quartzite, and I've got some misgivings, and it's possibly actually part of the Corella Formation. However, it provides some constraints. In contrast to the relatively thin interval of Ballara quartzite that you see in most places, to the east of Dobbin, there's a very thick succession up to a kilometre of sandstone, pebbly sandstones that directly overlie the Argilla Formation. It's a very sudden change probably across a fault, which I interpret as a growth fault or rifting at around the end of the Argilla Formation volcanism. This unit's referred to as the Crusader Sandstone member, but it's difficult to actually decide whether it's actually really part of the overlying Ballara quartzite or it's another unit that's not represented to the west. At the top of the sandstone, there's a distinctive ignimbrite unit, has quite large feldspar fragments, columnar jointing in places. It's been dated at 1770 million years. So it brackets the age of this sandstone package between 1770 and 1780, the age of the underlying Argilla Formation rhyolite. The ignimbrite's overlain by a relatively thin succession of quartzose sandstone, which seems to represent the typical Ballara quartzite, and that's in turn overlain by the Corella Formation. Further east, there's a long finger of outcrop that's generally referred to as the Bamara Horst. In it, the rocks are now assigned to a unit called the Bamara Metamorphics, and they're predominantly quartzite, but with some biotite schist and some felsic granophyls, and they're overlain by the Corella Formation. The quartzite-dominated succession may be equivalent to the Ballara quartzite, but it could also be the Crusader Sandstone member, and it represents an eastward continuation of that thickening that starts at Dobbin. The felsic granophyls has been dated. Gives a date of around 1775, and as well as that, there's a rhyolite that's also been dated. These ages are pretty much equivalent to the Argilla Formation, and suggest that this felsic granophyll is probably is the basal part of the Mara metamorphic sequence. The Corella Formation overlies the Boolarra quartzite apparently conformably, and it's the most widespread unit in the Merikathleen domain. In the lower grade part, it consists of calcareous siltstone, calcareous sandstones, and minor limestone. It passes into calc-silicate rocks, which are typical or characteristic of the Corella Formation. Most people's image of the Corella Formation are these big black calc-silicate outcrops. It also contains intervals of quartzose sandstone, and in places there are basalts and some rhyolite. Just some photos of typical low-grade calcareous siltstone in top, calc-silicates on the bottom left, and the example of the pillow basalts in the Lime Creek metabasalt member. Going east towards Cloncurry, there's lots of calc-silicate breccias, and an example of that is shown there. The rocks are commonly scapolitic, and that's led many people to suggest that the sequence includes evaporites or with an evaporitic carbonate shelf environment. However, the scapolite could also reflect saline metasomatism. There's extensive metasomatism throughout the Corella Formation, has resulted in albite, hematite, amphibole assemblages, which are generally referred to as red rock alteration. Of course, it's a chicken and egg thing. The saline fluids had to come from somewhere, and why not just from the evaporites in the sequence. In the area north of Merikathleen, there's actually a fairly coherent sequence. You can map out 4 distinctive unnamed members, but elsewhere this stratigraphy is not so well apparent. And even though the geophysics allows you to map various subunits based on radiometrics and magnetic response, these may be actually a metamorphic or a metasomatic overprint rather than real stratigraphic members. The main age constraints for the Corella Formation are the probable tuff that I mentioned, 1755 towards the base, either in the Corella or the underlying Boolarra quartzite. And traditionally the main constraint on the younger limit is the age of intrusions into it, like the Birstall granite, which occurred around 1740 million years. Detrital zircon ages have been a little bit uncooperative. They generally reflect the ages of the underlying units, like the Argilla Formation. So it's mostly around 1780, but we have been able to obtain a decent detrital age from the top of the sequence, and that's around 1740 million years, which is very close to the age of the intrusions, and indicates, well, for a start, it brackets the deposition of the Corella Formation between 1755 and 1740, but it also indicates that the deposition was pretty much ended at the time of the intrusion of these granites. Considering correlations to the western succession, this age is consistent with a correlation with the unit called the Kwalala Formation, which is the area shown in that bluey-green colour, and it has a maximum depositional age of around 1750 million years, so within that ballpark of the Corella Formation. Further east, and mostly under cover, there's a unit called the Mount Fort Constantine Volcanics, which hosts the mineralisation in the Ernest Henry deposit, and may be part of the late magmatic event in the Corella Formation. The published ages for the Mount Fort Constantine volcanics are also around 1740 million years. The volcanics consist of altered latites, dacites or rhyolites, something like that, and they're also volcanoclastic sandstones. The MDAs, as I sort of said, the MDAs and the ages of rhyolites in the Corella Formation and the Mount Fort Constantine volcanics are within error of the ages of the plutons that intrude the Corella Formation. And so there's only a short interval between the completion of deposition and the intrusion, or the intrusions may have actually caused the deposition to cease. East of the Mary Kathleen domain is a belt referred to as the Mitakuti domain. It abuts the Mary Kathleen domain. It's separated from it by the Pilgrim Fault, and the overhang fault is the eastern boundary of it, and it appears to be thrust northwards against the Tommy Creek domain. The succession in the Mitakuti domain can't be correlated exactly with the units that I've been talking about further west. And so it probably represents a separate, slightly later rift or graben. The oldest rocks in it are the felsic volcanics. They're very similar to the Argilla Formation. They're rhyolites, crystal-rich rhyolites, and also quartzo sandstones, but they've been dated at 20 million years younger. They're 1760 million years, and they're now referred to as the longer volcanics. They're generally a little bit more deformed than the ones that I've shown you from the Dobbin area, Kajabi area to the north. They have quite a well-developed foliation in places, and metamorphic muscovite and biotite. Overlying the longer volcanics is a thick pile of tholeiitic lavas, basalts called the Marrabar volcanics. There's some sediments also involved with the Marrabar volcanics. Lithologically and chemically, they're very similar to the Eastern Creek volcanics in the Western Succession, but they must be about 25 million years at least younger, and again, suggesting that the locus of rifting has moved eastward from the time of eruption of the Eastern Creek volcanics. The Marrabar volcanics are succeeded by the Mitakuti quartzite, a thick succession of sandstone and some thin basalt units, and also minor rhyolite. In this photograph, the valley between the two thick units of quartzite represents one of these basalt members. The rhyolite dated at 1755 million years, the same age as the tuff in the supposed Bellara quartzite. But the Mitakuti quartzite is thicker, probably by an order of magnitude, than the Bellara quartzite, and it's also generally quite felspathic rather than quartzose. The Mitakuti quartzite is succeeded by an enigmatic unit called the overhang jasperite, shown in dark blue around the edges of the Mitakuti domain. The unit is named because of distinctive jasperlitic siltstones that occur within the unit, although they're only a very minor component, probably only 1% or so, but they're quite interesting. They show quite dramatic isoclinal folds in places. But in the main, the unit consists of iron and manganese-rich siltstones, and also limestones, some of which are stromatolitic. The overhang jasperite also contains banded iron formations, and they were studied as part of an honours thesis by Alex Brown, who's now with Xstrata. He argued that they're certainly sedimentary, they're not metasomatic, but also that they were probably formed by so they're bacterial iron deposits, rather somewhat similar to calcareous stromatolites. The structures that he illustrates certainly look like stromatolites, but he's had difficulty convincing some people of this, and hasn't been able to publish this. The overhang jasperite may correlate with the at least part of the Corella Formation, presumably the lower part, but it certainly represents quite a distinctive environment and is restricted to this Mitakuti domain. At the northern end of the Mitakuti domain, there is a boundary that you can map between the jasperite and the Corella Formation, but the nature of the boundary is not clear. Moving east is the Maramo Staveley domain that abuts the Mitakuti domain along the overhang fault. The oldest rocks are the double-crossing metamorphics, which occur to the south in the Selwyn, or west of Selwyn. They're intruded by the Gin Creek granite, and they're probably in tectonic contact with the surrounding units, the Answer Slate and the Staveley Formation. Some people have suggested that the contact is a detachment. The metamorphics consist partly of gneiss and migmatite, particularly around the contact of the Gin Creek granite, but they grade outwards into chloritic metasiltstones, and there are minor sandstone and mafic rocks, including lavas. A maximum depositional age of around 1750 million years been obtained from a pebbly sandstone within the metamorphics. And that suggests a correlation with perhaps with the rocks in the Mitakuti domain, but at least it puts it within the Leichhardt superbasin. The younger age limit on the metamorphics is provided by 1740 million year ages on the Gin Creek granite, and also on the leucosomes within the gneisses. So that concludes a quick look through the Leichhardt superbasin, or the rocks in the eastern succession or eastern fold belt that are equivalent to the Leichhardt superbasin in the west. But there are some significant differences. Rocks equivalent to the guide supersequence, the lower part of the Leichhardt superbasin, are absent, or at least probably weren't deposited. The Argilla Formation represents the same rifting episode as the Eastern Creek volcanics, but is felsic, whereas the ECVs are entirely mafic. The relatively thin magnolin metabasalt may be equivalent to the ECVs and could be and were deposited outside the main rift. In the western succession, there's the Myalley supersequence that overlies the Eastern Creek volcanics. It doesn't appear to occur across at least across the Kalkadoon Leichhardt domain and the Merri-Kathleen domain, but the Crusader sandstone member that I talked about, and also the Bamara metamorphics, may be equivalent to it, but in a separate eastern deeper centre. The Quilala Formation, on the other hand, represented by the Lara quartzite and the Corella Formation, is more continuous across from the west to the east. The Corella Formation is probably more carbonate rich than the Quilala Formation, the Koala may represent the carbonate, may represent a more shoreward facies to the carbonate shelf of the Corella Formation. And as I mentioned, the succession in the Mitakuti domain, although temporarily equivalent to the Leichhardt superbasin, may represent a separate rift initiated somewhat later. The Merri-Kathleen domain is intruded by a large number of plutons that were previously divided into two main groups: the Wonga granites, shown in a sort of a magenta colour, and the Burstal granites and its related plutons in the warmer red. The Wonga granites were restricted to a strongly deformed belt, forming elongate plutons, mainly intruding the Argilla Formation. Mapping by BMR-GSQ and by Holcomb and Pearson from UQ in the 1980s subdivided the Wonga granites into a range of largely unnamed subunits based primarily on texture, and there were some relative intrusive ages that they could determine, but they're largely unnamed. Early shrimp dating suggested a range of ages from 1780 to 1740. The Birstall and granite and related plutons were generally less deformed, and they intruded higher in the sequence, so they were intruding into the Corella Formation. They were dated around 1740 million years. There's been a lot more dating recently by GSQ and JCU, and they refined the ages of the granites of the Mary Kathleen Belt, and they're subdivided into two main groups, but somewhat different to the earlier simple classification. The older granites are 1780 to 1775 million years. They're contemporaneous then with the Argilla Formation, and they've been assigned to a Argilla igneous province. Granites in the range 1740 to 1720 are assigned to a Wonga-Birstall igneous province, and includes the pluton shown as Birstall on this image, and many in the Wonga belt as well. As I've already mentioned, the ages on the Birstall granite have been one of the main constraints on limiting the age of the Corella Formation. The Wonga and Birstall granites were an integral part of the extensional subhorizontal detachment model of Holcomb, Oliver and Pearson. It was published in the early 1990s, and it was adopted by subsequent workers like George Gibson. In the model, the Birstall granite is depicted as being emplaced into a dilational zone within the upper plate, where the environment was more brittle compared with the lower plate. Intrusions were thus foliated and partitioned away from the, they were less foliated and partitioned away from the deformation related to the ongoing extension that gave rise to the Leichhardt superbasin. By comparison, the Wonga granites were intruded into the strongly foliated deformed zone, and they were deformed by the extensional deformation that was going on during their emplacement. Thus, the differences in the degree of foliation and deformation reflected the reflected space rather than time. The original shallow detachment that was part of this model was then thought to have been folded during the later isonorogeny. This model has been challenged by researchers at JCU in recent years, particular papers by Spencer et al. In Precambrian research, based on their studies of the Corella Formation and the timing of the granitoids that intrude the Corella Formation and the structures within it. They argue that that there was a significant multi-phase compressional event contemporaneous with amphibolite metamorphism and magmatism between 1740 and 1720 million years, and they term that the Wonga event or Wonga orogeny. They constrain D1 to between 1741 and 1735 million years, and D2 between 1735 and 1725. And think back to the double-crossing metamorphics in the Selwyn area, the deformation there would also probably be part of the early Wonga orogeny in this model. So now we move on to the Calvert superbasin succession, or their equivalents in the eastern fold belt. In the western part of the Mary Kathleen domain, the Corella Formation is overlain by the Dighton quartzite, probably disconformably. There's no angular break, at least in that area, and that's somewhat inconsistent with a widespread Wonga compressional event at this time. as I've just mentioned, proposed by JCU, suggesting that if there was this event, it must have been fairly partitioned into a fairly narrow local zone. The age of the lower part of the Dighton quartzite is not well constrained. The detrital zircons give more or less similar ages to what you find in the Corella Formation, but when you get towards the top, there is quite a distinctive younger age of around 17-15 million years, and you can correlate that probably with a magmatic event further to the northwest in the Fiery Creek volcanics and the Weber granite. And so the sedimentation, at least towards the top of the Dighton quartzite, was probably synchronous with that magmatism. The Dighton quartzite is part of the Mount Albert group, and other units assigned to this group crop out further east in the Mary Kathleen domain. These are the Knapdale quartzite, Cucurina Formation, Lady Clare dolomite, and a new unit called the Mount Roseby schist, which was previously mapped as Corella Formation, but it's the host rocks of the Dougal River zinc deposit. The Knapdale quartzite has a maximum depositional age of around 1710, 1715, consistent with it being post-Wonga, but also a correlative of the Dighton quartzite. It's actually a pink feldspathic sandstone, has cross beds and ripple marks, and in places there are mud crack sandstones. It's overlain to the west by the Cucurina Formation and in turn by the Lady Clare dolomite. To the east, the Mount Roseby schist may be partly correlative with those western units, and it seems to probably be it's been overthrust by the Knapdale quartzite. The Mount Roseby schist is dominantly metasiltstone and fine mica schist, flooded with scapolite. The grade increases southwards from this area shown in the map, and east of Mary Kathleen, it's represented by reasonably coarse-grained mica schists. A laminated metasiltstone has been dated just south of the Dougal River deposit, and its maximum depositional age was 1685 million years. There's an older model lead age on the Dougal River deposit itself, which is somewhat younger, around 1665 million years. So that may suggest that the rocks are actually of that age, if assuming that the lead in the ore deposit was derived from those sediments. The Cucurina Formation immediately to the west of the Knapdale quartzite is mainly carbonaceous siltstones, contains scapolite and tremolite, and it was a dolomitic siltstone. It's overlain by sandy dollostones and pyrititic dolomites, and some sandstones of the Lady Clare dolomite. Sandstone from the top of the Lady Clare dolomite has dated, and it's given a maximum depositional age of 1695 million years. That's within error of the age of the Mount Roseby schist. So it means it's all part of the one succession. These maximum depositional ages are like those from the prior supersequence in the western succession, and but given that you've got this younger model lead age, they could be younger, and in fact may correlate with the Gunn supersequence, which also includes the Mount Isa group, which is the host of the Mount Isa ore body. The Lady Clare dolomite could be, it looks like a fairly deeper water succession, and it may be a distal equivalent of the dolomitic Paradise Creek Formation in the western succession. So coming back further east again into the Maramo-Staveley domain and the Fig Tree Doherty domains, there's a unit called the Staveley Formation, which consists of locally calcareous sandstone and siltstone and occasionally some limestones. It becomes more metamorphosed as you go eastwards and grades into calc-silicate rocks. These were previously mapped as either a unit called the Doherty Formation or as Corella Formation. And it's superficially like the Corella Formation, but it's probably not as carbonate rich. The Staveley Formation is now mapped, includes large areas of calc-silicate breccia, particularly south of Cloncurry, and they're shown in the brown unit towards the top of the of that map. The origin of the breccias has been subject to a lot of study and debate, and there are probably multiple mechanisms for the brecciation. It may include fluid overpressuring, could even include salt diaparism if there are significant evaporites in the sequence. And the breccias have been mobilised and they actually intrude up into the younger Soldiers Cap group. Some example of the rocks, the coherent sandstone siltstone sequence. Often you get these arrays of orthogonal veins perpendicular to the bedding, and those rocks then pass often laterally into incoherent breccias. The higher grade rocks that were previously mapped as Doherty Formation occur to the east of Selwyn and Kuridala. They may have been more calcareous than the rest of the Staveley Formation. They're dominated by calc-silicate granophyls, but and if that's true, it may mean that, like the Koalala and Corella, you had a more siliciclastic shoreline facies passing into a carbonate shelf. But the rocks are very heavily metasomatized, and it's quite hard to tell the primary compositions of a lot of the rocks. The Staveley Formation actually has a gradational relationship with the overlying Roxmere quartzite in the Maramo area, and you have sort of thin bedded sandstones and limestones becoming thicker bedded as you go up the sequence, eventually passing into massive amalgamated sandstones that are more typical of the Roxmere quartzite. The tridal zircons from the Roxmere quartzite give ages of around 1710 to 1720, and suggest that, like the Knapdale and Dighton quartzite, they're derived from the Fiery Creek and Weber magmatic event. In fact, quartzite's a misnomer because the sandstones are quite volcaniclastic, consistent with a volcanic source. The tridal zircon of the relationship that I talked about between the Staveley and the Roxmere is probably the best evidence for the Staveley Formation being post the Wonga event and younger than the Corella Formation. But the tridal zircon data is a bit equivocal. When you've got a very large cluster there, and if you do a statistical unmixing, you get fairly consistent ages that look like the age of the Wonga event, but they also overlap with the maximum depositional ages of the Corella Formation. So it's a bit hard to know whether it's actually derived from the Wonga granites and recycled Corella, or whether it's the same age as a Corella. However, just looking at the if you take a different methodology to looking at the data and just do an inspection, there are quite a lot of younger zircons, and what I've done in the bottom figure is pooled all of the ages from the 4 samples of Staveley Formation of analyses where the 1 sigma error bar falls below the age of the Wonga event, and there's quite a large number of grains or analyses, and they have a weighted average of about 1720 million years, which is about the age of the Myubi igneous complex, which is one of the younger parts of the Wonga granite. So it suggests that the Staveley Formation and the rocks near quartzite are actually both part of the younger sequence post Wonga. So and looking at the supersequences in the west, that would probably fit in with what's called the big supersequence. The Staveley Formation in the Marimo-Staveley belt forms alternating belts with a unit called the Answer Slate. The Answer Slate's dominantly cleaved carbonaceous mudstone, and it only has very minor sandstone through it. Many of the contacts between the Staveley Formation and the Answer Slate were originally mapped as stratigraphic throughout the belt, and that led to all sorts of fairly conflicting stratigraphic relationships. But in fact, our interpretation is that all of the contacts are marked by faults defined by ferruginized and silicified zones, and they're probably folded thrusts. This is just an example of a part of the Marimo-Staveley belt showing all of these quite prominent ridges. If you delineate them, they're a sort of an interlacing network, and they may be oversteepened thrusts, or in a lot of cases, I think they seem to be folded thrusts when you map structures around them. An example of a ferruginized silicified ridge in the top panorama, and a quartzose myelinite along another contact in the bottom. The age constraints of the Answer Slate, the maximum depositional age is all suggested it's younger than 1700 million years, and the age is shown there in blue font, and there's a few cherty siltstones or probable tuffs that have been dated, give ages of around 1655, 1660 million years. So moving right to the east now, there's two units. There's the Soldier's Cap and Kuridala groups. They're broadly equivalent in age, both post probably 1690 million years. They're separated spatially by a belt of Staveley Formation, and also by granites of the Williams batholith in that area that's actually just shown as blank, but that accounts for their spatial separation. The Soldier's Cap group lies to the east of a major fault, the Konkori Fault. Soldier's Cap group consists of three units. And the lower two are turbiditic. There's the Llewellyn Creek Formation, which is relatively labile samopilites, and the Mount Norna quartzite, the thick bluish grey, relatively massive sandstone beds. The upper part of the group is the Till Creek volcanics, which consists of mafic lavas and carbonaceous siltstone, and all of the units are intruded by mafic sills. The sills and the lavas in the Till Creek are highly evolved iron-rich tholiites, commonly associated with thinned continental crust. Just some examples. The top left shows a graded samopilite where you've got the amount of andalusite increases to the top of the graded turbidite bed as the amount of mud increases. Quite a classic example of that reverse grading effect with metamorphism. The bottom left is the more massive sandstone beds in the Mount Norna quartzite. The Kuridala group, there have been three units subdivided into it. The Star-Cross Formation, which is again turbidites, lithologically similar to the Llewellyn Creek Formation, and it contains towards its top the New Hope sandstone member, which is felspathic sandstone, somewhat similar to the Mount Norna quartzite, although it's coarser grained and probably more proximal. The upper part is the Hampton slate, which is a black shale unit with mafic sills and possibly lavas. And it forms a top, and it's consistent correlation with the Tooll Creek volcanics. Again, some examples: carbonaceous metasiltstone at the top with some sillimanite porphyroblasts in the contact with one of the Williams granites, the thick-bedded sandstones of the New Hope, and a sequence of finding upward cycles in the Starcross Formation, where you've got massive, sharply defined sandstone beds at the base, grading up through more schistose rocks until you hit another sandstone interval. There's quite a wealth of isotopic data from the from the Soldiers Cap and Kurridala groups. So just a summary. So up on in the top part of the figure, the maximum depositional ages of the lower parts of both Kurridala and Soldiers Cap are generally in the range from around 1670, 1680 through to about 1700 or so. And the Hampton slate and the Tooll Creek volcanics have maximum depositional ages of around 1660 million years. But in the Hampton slate, the dolerite's been dated that's within error of that maximum depositional age. So it was probably intruded during the during or soon after sedimentation. The if you pool all the zircon ages from the Soldiers Cap group and the Kurridala group, and then play around with unmixing of the big population, which is all the younger stuff, there's the profile just show there's a blip around the Archean Proterozoic boundary coming from goodness knows where, and then there's almost nothing until after the Barramundi orogeny. So within that big population, you can statistically unmix it, and interestingly, when that happens, it pulls out all of the magmatic events that you see in the hinterland, including small amounts of the Leichhardt and Argilla, but then largely Wonga granites, the Fiery Creek Webbera, and then a younger population which probably corresponds with the Sabella batholith in the far west. In terms of correlations with the supersequences to the west, the isotopic constraints indicate that that most of the lower part of the Soldiers Cap and Kurridala groups were were deposited around the time when there was a high stand in the western part of the Mount Isa province, corresponding with the intrusion of the Sabella granite. So there's very little sedimentation over in the west. So these two groups indicate quite a different package. So the sediment was being washed right across the inlier and down onto the continental slope. However, at the time of the Hampton slate and the Tooll Creek volcanics and the carbonaceous slates of the Ansa, is a time of a maximum flooding surface that went right across the inliner, and that corresponds with all this mafic volcanism out in the east, and probably reflects the onset of thermal subsidence and a transient breakup of the Nuna supercontinent. This is a model put together by George Gibson, and it illustrates that to some extent. The Georgetown inlier in the east was pulled away, opening up possibly a marginal sea. There are similar age sediments in the Georgetown, similar age basalts, and so you had two facing passive margins on either side of what may have been a marginal sea. finally, going through the succession, the youngest rocks in the eastern succession are in this fairly enigmatic area called the Tommy Creek domain. It's been a bit of a puzzle for quite a while, but it consists of a fairly heterogeneous succession of quartzite, calcareous metasediments, carbonaceous metapelites, and mafic and felsic volcanic rocks. They were originally mapped as Corella Formation, but are now known to be much younger, and in fact are the youngest rocks in the whole of the eastern succession. They're in contact with high-level granite intrusions, the Tommy Creek microgranite, which are those folded sill-like bodies intruding the blue of the Corella Formation. The relatively young age was first demonstrated by dating a granule conglomerate that appeared to overlie the Tommy Creek microgranite. The detrital age of the sandstone or the conglomerate came out at around 1655 million years, or thereabouts. Anyway, within error of the age of the Tommy Creek microgranite, suggesting that the microgranite was the source of the sediment. But in any case, the whole succession had to be a lot younger than the Corella Formation. A recently completed study by Alex Brown for his PhD at JCU has further confirmed this. It's confirmed the date of around 1650 to 1650 for the lower part of the what are called the Milo beds, the main unit within the Tommy Creek area, and suggested possibly that there's an MDA of 1640 for a upper part of the sequence. Alex also identified a magmatic event around 1640 and multimodal suites of intrusive rocks and rhyolites and basalts, or dolerites, occurring around 1615 to 1620 million years. So the lower Milo beds may be partly equivalent to the Answer Slate and upper parts of the Soldiers Cap group, and also the Mount Isa and McNamara groups in the Western succession, but it may be somewhat younger as well. In any case, it was all deposited before the onset of the Isa orogeny, starting at around 1600 million years. The Isa orogeny is the sort of the terminal event for the whole of the for most of the Mount Isa province. It continued intermittently over at least 100 million years. There's some monazite dates from the Soldiers Cap group that suggest there may have been an early event around 1640 million years, which correlates roughly with the what's called the Riversley event up in the Lawn Hill area, but it's not certain what sort of event that was. Certainly the dates on the main high-grade metamorphic event is constrained by dates from Cannington on metamorphic rocks, titanite and zircon ages. Comes to between 1600 and 1585 million years. So that was probably when the main Isa orogeny started. And then there are monazite ages and zircon overgrowth giving a variety of younger ages right down to about 1500 million years. The Isa orogeny started with north-south shortening, generally characterised by zones of elevated strain and reverse reactivation of east-west trending normal faults, particularly in the Western succession. That you get that sort of thing. You don't identify these east-west faults so readily in the east. So in the east, the shortening occurred in a thin-skinned tectonic regime associated with significant northward translation of the successions along major myelinide zones. There were probably also large-scale naps. So in the Roxmere quartzite demonstrates this quite nicely in that you have separate areas of the Roxmere quartzite can be either, they're almost all flat, they're flat lying. Some are downward dipping and downward facing, and some are upward facing. So there were probably large recumbent folds. The later phase of the early Eisen orogeny changed to east-west or northwest-southeast shortening. The deformation style switched from the thin-skinned deformation to thick-skinned folds, upright, steeply inclined kilometre-scale regional folds, and north-south reverse faults and thrusts. And that induced the dominant structural grain that you see throughout the Isa province. With continued east-west shortening after it locked up, the deformation changed to strike-slip, oblique, and oblique faulting and regional wrenching. The later part of the Eisen orogeny saw the emplacement of lots of granites, starting off with 1550 with smaller trondhjemite, tonalite, granodite intrusions, but then succeeded by large batholiths of potassium-rich A-type granites that are assigned to the Williams supersuite and emplaced over about 40 million years between 1540 and 1500. The metamorphism in the Mount Isa inlier, it's writing it off with one slide seems not to do it justice, but basically it ranges from green schist facies to upper amphibolite. You have in a lot of alternating belts of green schist and amphibolite facies. The high in some of the belts, the grade also increases to the south. I've mentioned that the strain and deformation in the Chalcodone Leichhardt belt increases to the south, and in the Soldiers Cap group up near Cloncurry, the grade of metamorphism is green schist facies. By the time you get down to Cannington, it's upper amphibolite with migmatites. It's mostly of the low pressure type metamorphism, but there are higher pressure type conditions being documented in places in the Soldiers Cap domain. The other feature of the inlier is the metasomatism. Mike Rubenak is often says that the Mount Isa province is probably the most metasomatized belt on Earth. In various units, it occurred over a long period of time. In the Soldiers Cap group, it probably occurred over about 150 million years. In the Merikathleen domain, possibly as much as 250. It's moderate to high salinity fluids, derived possibly from evaporites in the Corella Staveley formations, but also probably a magmatic fluid component as well. It's structurally controlled. And igneous activity was probably an important driver, no matter where the fluids actually came from. The explosive release of the fluids related to intrusions was probably important in forming some of the breccias. And then the brine subsequently infiltrated those breccia zones and produced all the various alteration minerals, such as particularly albite, hematite, calcite, scapolite, and amphiboles. So I'll just finish with this is a revised time-space diagram in the style of that one of Blake's I showed you earlier, but the cover sequences have been replaced by these super basins, and the relationships between a lot of the stratigraphic units is now better constrained by the dating and by the mapping. And finally, I'll just acknowledge a host of people who've been involved in this and whose ideas I've borrowed, taken on board, and or disagreed with. So I'll leave it at that.
Thank you, Ian. Do we have any pressing questions?
Thanks, Ian, for that very comprehensive, detailed stratigraphic study. So I was curious if you used You didn't show any geochemistry. Has geochemistry been used at all to help support correlations?
It has been a lot. I haven't done much. There was quite a database of data, particularly on the volcanics and the granites. And I'd like to be able to get into it, but certainly, say between the Eastern Creek volcanics and the Magdalene and the Maribor, I mean, it has been published in general terms. There tends to be a progression from west to east, and then and certainly the basalts in the Soldier's Cap, those younger ones, are quite distinct from from those older basalts. So they're more mid-ocean ridge tholeite type
Yeah.
chemistry.
Yeah, okay.
Yeah, but Ian, you were looking around. You were going to comment.
Just reading the story.
Oh, okay,
I
yeah.
was going to say I published a paper on the discrimination of the various acid volcanic units back in the BMR journal back in, I don't know, 1870 something.
Thank you. Question at the back here from Mark.
Thank you, Ian. Just a quick query. Are there any emerging or new technologies that you can see or think about that are going to provide some greater insights into the geology of the Mount Isa district that haven't yet been applied?
Well, we could certainly use some different dating techniques, perhaps to date some of the. If we can date the basalt units, for instance, that would be a start. I mean, I'd like to date the Magdalene metabasalt, for example. If there are techniques other than detrital zircons that could be applied, I don't know, dating calcite or something like that in alteration might provide some constraints that and probably, probably more dating on the alteration and the metasomatism and so on. That could be quite an interesting story come out of that, because I mean it's gone on for 250 million years. It can't have been all continuous. There must have been episodes, and to know which ones actually related to mineralization would be that could be useful.
And what about geophysical techniques?
I don't know. It's probably not my field. I mean, there's I mean, we've mainly used the just the traditional magnetic and radiometric, certainly in the mapping. One technique that that actually did show this was the EM surveys that probably people haven't looked at much that have been done, and they certainly pick out units within, say, the carbonaceous units. For instance, we'd lump all of the siltstones in the Answer slate belt as just as Answer slate, but there was a thing that earlier mappers had called the agate down siltstone, and Alan Parsons had just ignored that and lumped it in. But in the EM data, it's completely non-conductive, whereas all of these carbonaceous things are quite conductive. So as you'd expect, so I've reinstated it. In fact, there are other areas through the Answer slate that that are non-conductive as well. So I mean that can help with the mapping, but
Thank you, Ian. Any last questions, or are we all thinking we want to get home
are there
before the
any?
next storms?
None on the.
None at home. They're all sated. I think they're had their dinner and now falling asleep. So I think on that bombshell, we'll thank Ian once again. And we'll see you all here in a month's time for the final talk for the year. Thanks all.